Hi, everyone. Let's talk about what you saw with the heat curve lab. Just to make sure that you saw everything that you needed to see, please take out the graph that you made during the lab. And I want you to add things to it as we go through stuff. So this is called a heat curve graph, heat curve. And this one is going to be specific to water. So that's what you used in lab. And so this first part of the graph has a signature shape to this. It's kind of like a stair step. So no matter what the substance is, you'll see the stair step type of shape. So that's the classic shape that you will see for this. Now the slopes might change a little bit. The length of these flat lines will change a little bit. At what temperature the flat lines occur will change, but the general shape stays the same. So you should have noticed as you heated or any substance, as it goes through the different states of matter, the temperature does not increase, it flatlines. That's the key thing to realize here. I notice a lot of you in the past years when I had students, a lot of you probably put down in your pre-lab that you thought the temperature was going to increase just directly, maybe exponentially. And you're thinking to yourself, why do I have to go through this? And the reason is because this is surprising. We don't have a temperature increase during a phase change. So let me start at the very beginning. You had solid ice. So solid ice looks like this here. So let's just review back to the activity that we've done before. This is solid ice. There's movement, there's vibration, it's moving. And when you put this on the stove or when you put this on a hot plate, you add heat, you're increasing the energy of the molecules. And eventually, it turns then into a new state. Now, this simulation doesn't do a good job with it. It definitely shows you the slope of it. If I go back to my solid, that this increase in this temperature goes really fast as a solid. And once I get into liquid state, it kind of slows down the rate, but it doesn't flatline at its melting point, which should be 0. So let's go back to this. So as this increases a pretty steep slope here, all I'm doing is increasing the motion of this. Let me get my pen back here. So increasing the motion or the vibration that's happening. All right, so it increases that. So these guys are just vibrating more and more and more and more, but still in that solid shape, still stays the same shape, keeps the same shape, and it keeps the same volume. All that is constant. And then right when it hits 0, instead of increasing temperature, all that energy is going in to do something. And so we're going to go through the why a little bit later, but this is going to be a phase change right here. This area here and this area here are your phase changes. So that's your melting. So here's our melting point at 0. So anytime you see that flat line on a graph, you can determine the melting point by just going over to the y-axis and looking at the number that's there. So the melting point of water is 0. Sometimes we're going to be eventually getting back to this, but heat of fusion, so you might hear something about fusion with this phase change. Then once you're in the liquid states, and I'll go back to this animation here, you're in the liquid state here, you're rolling around, you definitely have more motion to it, but these molecules are still pretty stuck together. Like they're stuck here in distinct rings. They're pretty much stuck here, a little bit loose, more loose, not quite as stuck together. So there's these forces of attraction between these molecules, and they get a little bit more loose here as you get more energy. And as I increase the temperature here in the liquid, it just move faster and faster and faster until eventually some of them break away, and then we start doing a phase change. And that phase change happens at 100 degrees Celsius, and eventually the gas will start looking like this. So we increase, again, increasing motion is what's happening here. All that heat energy is going to increase the motion, so they're rolling around more. Here, and it's moving faster and faster. It's getting hotter and hotter, right? And then when you hit 100 for water, now it's going to be different for a different substance, you're going to hit the boiling point, and then you go through that phase change. You vaporize, you turn into a vapor or a gas, you boil. So that would be going from this liquid state to the gas or vapor state up here. As you hit the vapor, it just continues to increase and gets really, really, really hot. So you can get dangerous levels, almost to the point where you could like set paper on fire. So Let's talk more about these flat lines, which are really important. Those are the phase changes. And what is the energy doing? The energy that you're putting in, because you constantly just had the same setting on your hot plates, same setting on your stove, you're constantly putting the same amount of energy in, that energy is going to break what we call these forces of attraction. And later on, we're going to call them IMFs. You don't have to know them. Oops, I'm out of room here. IMFs. You don't have to know them now, but IMFs is what we're going to be dealing with a little bit, like many chapters from now. We're kind of at the very beginning of things. So IMFs, intermolecular forces. So if you see that term, that's what that means. But it's just to break these forces of attraction between molecules. And you need to break those forces of attraction so you can change states. So the energy is going to break force of attraction between molecules to change the state of matter. So let's look at this animation again. So you have the solid and the energy. Again, don't look at the temperature here because I don't do the flat line part. But when I do hit the 100 and change, all that energy is breaking that force of attraction down. And when we just increase the motion of this. And eventually, when we get to the gas, you have to break all those forces of attraction apart again. Just to kind of prove to you that like water molecules like stick together, I thought this was a very good like demonstration of it. Putting drops, surface tension of water, putting drops in a penny. And you can see here, as this goes forward here, you can see it really bead up. And these water molecules are sticking together so they don't roll off the side of the penny. Now, every substance is a little bit different. Water has a very high surface tension. They're very, very sticky because they have strong forces of attraction. You can put quite a bit of drops on a penny, and you can really see it just like right here beating up and not rolling off. If this was a different substance, it would probably just run off the side. You couldn't put very many drops on top of the penny for this, so that you can really bead this up. I have a little animation of this over here. So if I add drops of water, you can see how they kind of stick together and they kind of stay on top. Now, if I switch this out with a different type of substance, say something that wasn't very sticky. So this has a lot of IMFs or intermolecular forces. So all these molecules are kind of stuck together. If I had something with not very much like hexane, if I put a drop down here, it just kind of spreads out. It won't beat up because they don't stick together and they just kind of run off right away. So that would be just comparing and contrasting how sticky the molecules are. So to apply that to this, as I draw, say, hexane, I get the information about the melting point and boiling points of hexane up here. If I were to draw that picture, so let me just draw a quick graph here. So say I'd redraw this water. So let me just say this baseline is water. So this would be at 0 degrees Celsius, and this flat line would be at 100 degrees Celsius for water. So it'd be H2O. If I was hexane, if you look at these numbers, negative 95 degrees Celsius is where it melts. So it's much, much lower. So let me do a different color here. So that means, so say, negative 95 is way down here. So I could be like way lower here. It probably wouldn't take very much energy if I'm not stuck together. It wouldn't take very much energy to break it apart. So I might make that line a little bit shorter too. But it's definitely lower. And then it would go into its liquid states. And then at 69 degrees, so somewhere in here is where it would break apart, use all its energy to break apart the molecules into a gas state, and then it would increase from there. All right, so this is hexane for this. So this is not sticky. It has very weak force of attraction or hardly any force of attraction. And then you have your water, which is sticky. The molecules stick together. It has very strong force of attraction. So you can see how the difference in the melting points are there, and the boiling points, and you can see the difference in like maybe the length of the line, how much energy you have to put in. But the shape is basically the same for that. So in the moral of the story here, again, you can look at the shape, you can just figure out that if you see the two flat lines, you know that first flat line must be its melting point. So below it's the solid, then will come the liquid, then the gas states. The flat lines represent the phase change. So this would be melting, this would be boiling or vaporization. When you hit that flat line, you can go over to the y-axis and determine the melting points or the boiling point for the substance. And again, the reason why it flatlines is all that energy is going in to break these weak forces of attraction between molecules. So the molecules get stuck together. They're really stuck together as a solid. Then some of those force of attraction are broken so they can kind of start rolling around. So that energy goes to break all those so they can roll. And then you break like all of them apart to get them into a gas state. All right, so good luck with the questions for this. Please email me if you have questions.